Okay, so course of probability number 8, we start continuous random variables. Okay. So continuous random variables will be random variables. And we have already seen some facts concerning random variables that are true in grid generality. Okay? So it's the objective of the remainder of the first slide, okay? Together, we have seen the definition 11 and the proposition 8 before. Okay, that was just before to start the case of the discrete random variable. We have together the distribution function, okay, of a random variable, and without any type of hypothesis, just being a random variable with values in R. Okay. I have also defined the quantile, but I will come back on this point during the statistical part. Okay. And we have seen together, I have proved some of them, okay, not all of them. Typically, if I remind, I have proved the 3 first, okay, and you have the proof of the 3 last statements of proposition 8, okay, in the list 1 of proofs, okay. And from today, we are going to start the list number 2 of proofs concerning the course, okay, if you are interested in. So we have seen that the distribution function is between 0 and 1, because it is a probability. We have a distribution function that is increasing, because the probability is increasing. If A is included in B, P of A is less than P of B, okay? It is possible to recover the probability that X is strictly greater than A and less than B from the distribution function, something that I have proved. And I have other properties, limit in minus infinity 0, limit in plus infinity 1, right continuous, and the fact that if I ask you the distribution of someone, okay, well, the distribution function characterizes perfectly the distribution. Okay, so if you have 2 random variables having the same distribution function, they will have the same distribution. If I am in the discrete case, if they have the same distribution, they will have the same probability mass function. Okay? So it is what we have already seen together. During the previous session, we have spent time on the discrete case. And in the discrete case, it is a little bit particular because what I have in the discrete case, so discrete means that my set of possible values is countable. Okay? So x of omega is countable. And I have decided, okay, to represent this one, okay, so the range, by the set of the possible values this way where capital I is countable. Okay? And I have supposed that I have ordered these possible values. Okay? That is xi minus 1 is strictly less than xi and so on. So I am in this situation here. I have xi minus 1 and xi, and if I am discrete, I don't take any value between xi minus 1 and xi. Okay? It's the advantage to be discrete. So if I come back to the previous proposition, okay, the probability that x is less or equal and xi is strictly greater than xi minus 1, just applying the formula number 3 in the proposition 8, I obtain the probability that x is less than xi minus the probability that x is less than xi minus 1. Okay? And in fact, so here I have the difference between, okay, the distribution function at the 2 points. And what is this one in the discrete case? So keep in mind that we are in this situation, no values between. So what is the meaning of being less or equal to xi and strictly greater than xi minus 1 here? It's exactly the probability that x is equal to xi because I don't take values, okay, strictly between the 2 points. So I see that from the distribution function in this particular case, that is the case of discrete random variable, something that won't be true in what we are going to see now, but in the discrete case, I recover easily the probability mass function from the distribution function. Okay? Something, I repeat, that will and that won't be true in what we are going to see today. Okay? So today we are going to spend time on continuous random variable, and we are going to see just now what is the definition of being continuous for a random variable. So be careful, huh? It's not continuity in the sense of analysis you classically do. Okay? A mapping that is continuous, okay, in the classical sense, means that if you have un that converges toward L, f of un converges toward f of L. It's not this notion here. It's continuity in the sense of random variables. Okay? So I have this in the discrete case, so probability mass function may be recovered from the distribution function. And now, definition 15, that is the definition of being continuous for a random variable. Okay, if I come back to the discrete case here, and let's do a picture. So if I do a picture of the distribution function, I can do a picture like this, because I know that my values are between 0 and 1, okay, that my set of possible values for the set of definition is world R, okay? So what happened? In the case of a distribution function. Okay, so let's suppose that, so it's a picture I have already done, okay? So you have something this way. So you have something that will be this way. I have a jump at the set of the possible values. It's a little picture I have already done in order to show you how to plot a distribution function. So I have something this way for a distribution function, and I see that in the discrete case, in this case, since I don't take values strictly between xi minus 1 and xi, I have a jump at all the points that are the possible values of the discrete random variable. Okay? So in the discrete case, when I plot a distribution function, I have jumps, meaning that this mapping, in the sense of classical analysis, is not continuous because it has jumps. Okay? A continuous random variable will just be a random variable such that the distribution function is continuous, meaning that I can't be in this situation. Okay? So you have the definition 15. A random variable is continuous if the distribution function is continuous. So continuous here will be in the sense of random variable, and the continuity notion here is the continuity for classical mappings. Okay, the continuity you know. There is a consequence to this definition. A priori, a consequence that is a little bit strange. That is, for any real number, the probability that x take a very particular value is always equal to 0. Meaning that a continuous random variable, it doesn't imply that x is always equal to 0. But the probability that I take a particular value is 0. Why I have this? I have this because of the following. I am interested in, okay, the value small x. Okay? And I say that, in fact, I can write, the idea is, in fact, to use, of course, the definition, that is the continuity, and to use the statement 3 here, this one. The singleton x may be written in the following way. It's an intersection for n belonging to n star of the following intervals that are intervals of this form here. Here you have the interval AB open at A and close at B. Okay? And the idea is to express my singleton using this type of intervals. So I can write this way. So I want it to be inside this one. Why I have this? So if you do a picture, you have x minus 1 over n, this way. If n goes to plus infinity, I will have smaller and smaller intervals when n increase, okay? So for example, for n equal to 1, you have x minus 1. For n equal to 2, you have x minus 1 half, x minus 1 over 3. So you have smaller and smaller intervals. And at the end, since 1 over n goes to 0, the only point that is in all the interval is the point small x, okay? So I can write this one as this intersection where here you have a decreasing sequence of sets. Decreasing sequence of sets, okay? Do you agree with what I have said here? But I have a result in the course, okay? A result of a proposition that I don't have used, and that tell me that in the case of probability, I have several situations where I am able to compute probability of the union of pairwise Dijon set is equal to the sum of the probabilities. It's the first thing I am able to do. Second thing, if I have an increasing sequence of sets, the limit of the probabilities is the probability of the union. Something we have seen together. Last statement, if I have a decreasing sequence of sets, the probability of the intersection is equal to the limit of the probabilities. Okay? So if I apply this result, that is a result concerning from the first part of the course, the probability that x is equal to small x, using what I have written here, is just the limit when n goes to plus infinity of the probability that x belongs to this interval, that is exactly this one. Okay, so I don't have in mind the proposition, but it's the first part of the course when I have defined what is a probability and the consequence of the sigma additivity statement. First part of the course. But I am happy to have this kind of thing because I know that I can express this type of probability using the statement 3 here. Okay? So it's the limit when n goes to plus infinity of what? Fx of small x minus fx of x minus 1 over n. And what happened for this difference? Keep in mind that you have a statement, you have a property, and we are in the case where we suppose that the distribution function is continuous. So, what is the limit of what I have inside here? X, and so the difference converges toward 0. Because fx is continuous. C0 means continuous. And so I have what I want. That is what I have in red in the slides here. Okay? So in the case of continuous random variable, the probability to take a particular value is always equal to 0. Okay? And we have some advantages in order to do this. Because typically, if I am in the discrete case, since the probability to take particular values may be strictly positive, I have to be careful when I consider these three different probabilities. In the discrete case, it is very important to know if x is inside the interval or not, or if a is inside the interval or not. But what is interesting is that in the continuous case, I don't mind, because the probability to take one value is always 0. So you have the equality between all these probabilities. Okay? Because the probability that x is equal to b is equal to 0, so I have the equality between both. And here, I have the probability that x is equal to a and the probability that x is equal to b, that is 0, and so I have the equality between these two. So it means that when you have to compute the probability that x belongs to an interval in the continuous case, you don't mind about the bound of the interval. Okay? Something that is really different than what happened in the discrete case. Okay? So it's important, and this one, okay, keep in mind that it is in this case, not in grid generality. Okay? So this is one of the major consequences of being continuous for a random variable. Okay? The probability that x is equal to small x is always equal to 0, but of course, this kind of probability will be in general strictly positive. So in fact, for continuous random variable, we will be interested in the probability that x belongs to an interval and not the probability that x is equal to one particular point. Okay? So this is the definition of being continuous for a random variable. Are you okay with this definition? Clear for everybody? So make the difference between the two cases, okay? Because in general, the strategy we use in order to deal with these two different problems are different typically. I don't mind about points in the continuous case, okay? Something that is totally false in the discrete one. Okay. Now, in this course, we are going to focus mainly on particular continuous random variable, the one having a density function. And first of all, before to define what is random variable having a density function, I define what is a density function. Okay? So a density function is a mapping, okay, from R into R that fulfills three conditions. So if I ask you to prove that someone is a density function, you have to prove first that is something that is positive in the large sense, always positive, not necessarily strictly positive, but positive, okay? I want you to prove that you have a mapping that is continuous in the classical sense, okay, that is without jumps, not necessarily everywhere, but on whole R, except for a finite number of points. Okay, so it means that you can have jumps in a density function, but not that much. Okay, and for us it will be a finite number of points, so of jumps. 1, 2, 3, in general it will be 1 or 2, okay, in the examples we are going to see together. Okay, so you have to prove that I don't have jumps except for a finite number of possible jumps. Okay. And what is more, I want that the integral, so this is the Riemann integral of this mapping, okay, is equal to 1. That's why in the prerequisite I have said to you it's important to be able to compute integral for this course, because the 2 next or 3 next week we are going to compute integrals every time. My course is not a course of computations of integrals, it's a course of probability, so computing integral will be a tool I want you to be fluent with. Okay? So the integral is equal to 1. So just a little remark concerning this notation with the plus and minus infinity. Okay? What I mean and what I will mean during the whole course, and it's something, so you have a little document I have written, okay, that is reminder on Riemann integral, where you have all the things, okay? What I mean by this one, okay, so what is an integral with infinite bounds? Well, it's just the limit of an integral with finite bounds, okay? As an infinite sum is just the limit of the partial sums. So by this one, I mean, for example, the limit when capital A goes to plus infinity, or this one. So here you have a classical Riemann integral, okay, on minus a. If you make a goes to plus infinity, what I mean by this integral is just the limit of this one, okay? So maybe at the beginning, okay, to compute this kind of things, we are going to come back to this definition, but let's say in 10 minutes, okay, we won't do this, okay? We will have in mind directly this definition and handle directly this kind of objects, okay? And keep in mind that since I have a limit, sometimes this limit doesn't exist, okay? It's possible. I can show you, okay, examples, and you have examples in my document where the integral of someone between minus infinity and plus infinity is not defined, in fact, okay? Or maybe the infinity. But it is possible not to be able to define this integral. But in the case of density function, no problem, because I impose the integral to be 1, okay? So I repeat, if I want to show you to prove that something is a density function, prove that it is positive. Something that is not complicated in general, okay? Continuous except at a finite number of points. And what you are going to use, you are going to use the pool of all the continuous mapping you know. Exponential, logarithm, okay, polynomials, and so on. Okay? All the ones that you know that they are continuous. Okay? And if we have jumps, it will be only at a finite number of points. And finally, integral equal to 1. So you will have to compute an integral and prove that it is equal to 1 if you want to prove that I have a density function. So let's see an example. An example that will be involved in the definition of the uniform distribution, but in the continuous case. For the moment, we have defined the uniform distribution for a finite number of elements and say that the probability of each element is equal to 1 over the total number of elements. In the case of the uniform distribution, okay, I will define it through its density function, the density function that will be exactly this one. Okay, so what I have defined here, I have f of x. You see something when I write in red, it's okay? Or you prefer me to use the... So tell me, huh? I don't know. Because me, I am at 20 centimeters of the board, so I can see the red perfectly, okay? But I will use the white one and I will just underline with the red, okay? So I define f of x in the following way. Indicator function of the interval AB over B minus A. And if I want to make this one compatible with my definition, I impose B to be strictly greater than A. Okay? If I plot this density function, what I have? If I am outside the interval AB, so suppose that you have A and B here. If I am outside the interval AB, my value is 0 because I have an indicator function. 1 if I belong to, 0 otherwise. So if I don't belong to the interval, 0. So you have something like this. Okay? This way. No. I exclude A and B. Okay? So 0 if I am strictly less than A, 0 if I am strictly greater than B. And what happens if I am inside? What is my value? So between A and B, I obtain what? 1. 1 for the indicator function, but you divide by B minus A. Okay, so you have 1 over B minus A. Okay? B minus A, that is a strictly positive number. So you have here B minus A, and you have something with value B minus A. So I'll try to plot correctly. Okay? Something like this. Okay? Clear? Indicator function is 1 if I belong to the interval, and I divide by BO. Excuse me. Tell me if you have some remark. It's 1 over. Okay? Don't hesitate to tell me. Sometimes I do misprint. Okay? So I have 1 over B minus A. Not B minus A. Because the indicator function in the interval is equal to 1. So let's check that what I have defined here is a density function. So the fact that it is positive, I have nothing to say, it's because B is strictly greater than A, so I have something that is positive as I have plot here, okay, always positive, but in the large sense, it can be 0, but whatever, okay. Continuous except at a finite number of points, well, it's exactly what I have here, because I have only 2 jumps, jumps at small a, jumps at small b, okay. And here I have a constant, a constant, a constant, so all mappings that are continuous, basically. Okay. So I am continuous except at small a and except at small b. And if I want to compute my integral, what is an integral in this basic situation here? What is the intuitive meaning you have below the integral? Integral corresponds to a concrete thing, in fact. What is this concrete thing? Area, okay? here my integral is simply, okay, the area of this rectangle. And so my integral between minus and plus infinity in this case is what? It's simply the integral between a and b of 1 over b minus a dx. That is exactly the area of this rectangle. And what is the area of this rectangle? 1. I have done the job for having it. So you have here a typical and very basic example, okay, of what may be a density function. And you will see in a few seconds that this is the way we define the uniform distribution on an interval, okay? So I prove, okay, that I am positive, continuous except at a, except at b, with an integral that is equal to 1, because here the integral is just represented by the area between the curve and the x-axis, okay? Because there's something that is positive. It's clear for everybody? So, I know what is a density. Since I know what is a density, I can define what is to be a random variable having a density function. Okay? So I know what is a density function, and now we are going to define what is a random variable that has a density function. But it's typically the definition 17 here. When we say that a random variable has a density function, when the distribution function may be obtained from the partial integrals of a mapping that is a density function. So x, so I'll write it this way, f of x is the density function of capital X if you have something to prove. It's not true in general. Typically in the discrete case it won't be possible to have a density function. Okay? If what? If by the distribution function of x, that is the probability that x is less than small x, in order to compute the probability that I am less than x, you have just to compute the integral between minus infinity and x of the density function. Now be careful when you use integral, okay? Typically integral having a parameter in the bounds. In general, that's why I have used small u here and not small x, because you have an x in the bounds. Try not to use the same name for the variable of integration and the other variable you deal with, okay? Don't put an x here and an x here. If you write, it's okay, because you have the variable of integration and what you have in the bounds, so a priori you can give the name you want to this one, u, z, t, what you want, okay? But in order to avoid mistakes, in general, we use different notation for the variable of integration and what I have in the bounds here, okay? So that's why I can use u or I can s this one, for example, whatever. The name of this variable doesn't matter in the computation of the integral. So this is the definition of having a density function for a random variable. And of course, fx is the density function of x if I have this, and f of x fulfills the previous definition, that is to be a density function this way. And this one. Okay? So in general, okay, if I ask you to prove that someone has a density function at the very beginning of this part of the course, okay, what you will do, you will consider its distribution function, and you will prove it, if it is possible to write it this way. Okay? But it is not the most convenient way to do, so that's why we have some alternative result that will help us to do this one, okay, in a better way, let's say. So are you okay with the definition? So the distribution function, okay, is this one. Okay? typically, just a remark, if I want to compute this in this situation, what will you do? What is this? If you suppose that you are in the statement of definition 17, that you have a density function, how to compute this kind of probabilities here? So just to show you that this one, we know that from the statement here 3, that it's the distribution function b minus the distribution function a. And here I repeat that I don't mind, so you can put this one, okay, this one, all the case you want, okay, it gives rise to exactly the same probability. I don't mind about bounds in the case of a continuous random variable. Okay, so you have this one, you have also this one, and this one, you have this one and this one, and you have all the possible cases here. Okay. From my preceding relation here, I know that this one is the integral between minus infinity and b, minus the integral between minus infinity and a. And so, what is this one? Because b is strictly greater than a here, but it's what we call the Schall relation for the integrals. Okay, so this is just the integral between a and b. Okay? So when you want to compute the probability that x belongs to an interval, okay, but you just have to compute the integral of the density function over this interval. Okay? So I erase this example. I will come back on in a few minutes. Questions? So if you have questions, ask me. Questions? Sure? Okay for everybody? So I have this. Now a proposition that we are going to use several times in a few minutes. Okay, that is how to pass concretely from a distribution function to a density. Okay, so you have already an answer. That is, the distribution function is the partial integral of a density function. But in general, okay, if you start from this one and try to prove that you can put it on this form, it may be a little bit tricky in practice. Okay, so we are going to have other ways to do, just using basically the definition. Okay, so it's the aim of the proposition 12. Okay, that make the link, in fact, in most of the situations, between the density function and the derivative of the distribution function. Okay? So I said the following. You have two statements in this proposition. So I suppose that I am in this situation here. Okay? I suppose that I have a random variable having a density function. Okay? This way. If I suppose that the density function is continuous everywhere, okay? Because in my definition, I can be continuous except at a finite number of points. Here I suppose that A is equal to the empty set. Continuous everywhere, okay? Continuous. I said that if you want to recover the density function from the distribution function, what I have to do, here you have an integral depending on the upper bound. And it's a result, I hope you know, that when you compute the derivative of an integral depending on the upper bound, what do you obtain? What you have inside the integral. Okay? When I compute the derivative, so the result I use here is the fact that if you have something like this, let's say f of u du, with f continuous. But if f is continuous, in fact, when you compute the partial integral, you obtain a mapping that has more regularity than small f. And we can say that it has one more regularity. That is, here f is C1. What is the meaning of being C1? That is f differentiable and f prime continuous. So C1 means that the first derivative exists and is continuous. Okay, it's something that we are going to use several times in this part. And a notation that you use in analysis, that you use in optimization, and so on. It's not new for you. F is C1, meaning that f is differentiable and the derivative is continuous. And if I want to compute concretely its derivative, and the derivative is equal to what I have inside the integral. Okay? So it's what you can call as one of the fundamental theorem of analysis. Okay? But if I am here in the statement A of proposition 12, I am exactly in this situation. I suppose that I have this relation, and I said that in order to recover the density function, since the density function is related to the distribution function as distribution function is equal to the partial integral of the density function between minus infinity and x, then in order to recover what I have below the integral, I just have to compute the derivative according to the result I have written on the board. Okay? So if you know that you have a density function, in order to find concretely this density function, one possible way will be to compute the derivative of the distribution function if you know it. It's one possible way. So if I have the density function, then this density function is the derivative of the distribution function. Statement B is a kind of reciprocal of this result here. It tells me the following. So suppose that you don't know if the random variable has a density function or not. The only thing you have is the distribution function. So I give you a distribution function, and you want to know if this distribution function is related to a density function or not. You can do the following. If you prove that fx is continuous, so not necessarily everywhere, but on R except a finite number of points, then x has, so I repeat, it's not clear what I have said. If you suppose that the distribution function is continuous, okay? Distribution function continuous. Of course, because we are going to be in the case where I have continuous random variables, and the definition of being continuous for a random variable is just my distribution function is continuous. So I suppose this, and I suppose that f of x is a little bit more regular than to be only continuous. I suppose it to be C1, that is differentiable with a derivative that is continuous, not on whole R, but on R except a finite number of points. So I want to be continuous everywhere, and I want to be C1 on R except a finite number of points. In this situation, if you prove that the distribution function has this regularity, then you will obtain the density function as the derivative of the distribution function. So be careful, it's not the same kind of result here. First statement, you know that you have a density function, you want to obtain it from the distribution function. I compute the derivative of the distribution function. Second statement, you have a random variable, you don't know if it has a density, but you remark that the distribution function is regular, let's say, and so you can obtain the density from the derivative of the distribution function. So at the end, of course, the derivative is always, the density function is always the derivative of the distribution function here, but in one case, I suppose to have a density, in the second one, I prove that I have a density. Okay? And I have explicitly the density. So for the density, it's the derivative, but the density, the derivative is not defined everywhere because I am only differentiable on R except a finite number of points. Whatever, the density will be this one on R minus A and 0 otherwise. So where you are able to compute the derivative, the density will take these values. For the other cases, okay, you put 0. Okay? And we are going to see several examples of this situation, okay, in the few minutes. So I have this integral relation between distribution function and density, okay. If I have this relation, and if the density is continuous, to obtain it, I can compute the derivative. And if I give you a distribution function, if you prove that it is sufficiently regular, you will be able to obtain the density just computing derivatives. So in this proposition, in fact, the idea is just to compute derivative of distribution function in order to obtain density. Okay? And this result, I repeat, comes from this one. And this one just comes from the fact that you have a relation between the derivative and the integral that may be the derivative of the integral depending on the upper bound is equal to what I have below the integral, but you have also that the integral of the derivative is equal to the mapping itself. That is, the primitive of a derivative is the mapping itself. Okay? So a priori, nothing complicated from a theoretical point of view. Okay? So don't worry, we are going to exercise concerning this proposition in a few minutes. Okay? But for the moment, I want you to see classical situation. In the discrete case, for me, classical situations are uniform, binomial, Bernoulli, Poisson geometric. In the case of continuous case, okay, at the beginning, at the very least, it will be uniform, exponential, and Gaussian, okay, distribution, that we are going to see the definition now. And you will see that we are going also to spend time on what we call the gamma distribution, okay, in at least 5 of exercises, okay. And it will also be considered as an important distribution for the course. Okay. So I have this one, but I have already done the job for this one, okay. I said what? If I have B strictly greater than A, a random variable is said to be a uniform random variable on the interval AB. Okay. And I use this notation. X follows a uniform on the interval AB. If I have this one, so just be careful because there is a misprint here. So have a look on the slide, everybody. Have a look on the slide. So here, so it changed nothing. But if I want to be in coherence with what I have said before, here it's strictly greater or equal to A, and here strictly greater or equal to X. Okay? You put a large inequality here. Not a strict. It changed absolutely nothing, okay, in the definition of the density because you don't mind about points, as I have said to you, okay. But if I want to cope with what I have said to you here A and B are inside the interval, okay. So if I want to have the same definition, so change this one in the slide number 6 in the definition of f capital X. You have I am equal to 1 over B minus A if X is greater or equal to A and less or equal to B. Okay? From a technical point of view, it changed nothing. It's just to cope with the preceding example I have given to you. So, if I make this little change here, we have already proved together that here you have a density function because it is positive, continuous except at A and B, and with an integral equal to 1. Okay? And I said that a random variable follows a uniform on the interval AB if it has this density function. Okay? So I want to compute the distribution function in this situation. So that is, I am interested in this quantity for this particular situation. Okay? So if I come back to my definition here, the distribution function is just the integral of the density function. And here, the density function is given by the first formula in blue here. My idea is, are you able to give me what is the general formula for this distribution function? First, I can remark that if I compute this integral between minus infinity and x, what happens, okay, if x is strictly less than A. 0, because what I have inside is always 0. Okay, so I have several situations. It's 0 if x strictly less than A, because this mapping is 0 when I am strictly less than A. What happens if I am strictly greater than B? Not 0. It's not possible for a distribution function to have values for big X that is 0. You know that the limit of the distribution function in plus infinity is 1. Okay, so if it is constant for big X, it will be 1, not 0. Okay, so if X is strictly greater than B, in fact, the integral I am interested in is just the integral between A and B, because A and B is the interval on which I am not 0. So here it's just the integral between A and B of 1 over B minus E du, that is equal to 1. So I start to be always equal to 0. I finish to be always equal to 1. I repeat, if you find 0 here, it's meaningless. A distribution function can't have a limit equal to 0 in plus infinity. It's 1, its limit. Okay? So if it is constant at the end, it will be 1. If it is constant at the beginning, the constant will be 0 for sure. Okay? It's not possible to have other cases. And now I am in the situation where x is between A and B. Okay? And what is the integral between minus infinity and x in this situation? But it's just the integral between A and small x of fx of u du. And I will continue the computation here. Okay, if x is between A and B, when I compute the integral between minus infinity and x, in fact, the only points where my density function is not 0 is between A and small x, because x is between A and B. So don't do too much break between two breaks, because the course will be transformed in breaks if you do this, okay? So not for you, it's for, because I have seen some students disappear during the course, okay? So if you have an emergency, for sure you can go out, okay? But I do breaks, so let's say that don't do breaks between breaks, okay? Or I will be a teacher of breaks, in fact, and it's not what I want to do. Okay? You don't need me to do breaks, okay? Maybe a little to do probability and statistics. So I want to compute this one. So what is the value of f if I am between A and x? But it is 1 over b minus a, simply. And so what is this integral? It's the integral of a constant mapping over this interval. And I obtain x minus a over b minus a. Okay? So I have here x minus a over b minus a, and it's exactly what I have written here. If I am, okay, strictly less than a, I am 0. If I am greater than b, I am equal to 1 using this indicator function here. And if I am between both of them, it's equal to this quantity, exactly the one I have here. Okay? So I see that I have, a priori, 3 parts for the definition, but of course, be careful, because you know that you have a density function, so the distribution function has to be continuous. Meaning that even if I have the 3 parts, okay, I don't want jumps. And in fact, I don't have jumps, because if you take this expression, for x equal to a, that is the lower boundary of the interval, okay, what is the value for x equal to a of this one? 0, of course, no jumps. And for x equal to b, 1, of course, because I don't want jumps. So if I try to plot this distribution function, okay, here, 1 is 1, okay, and I suppose that I have AB this way. But before A, I am 0, After B, I am 1. And between, it is the equation of what? This one. Of a line. And I don't have the choice because it's a line and it has to be continuous. So you plot this one. Okay? You have here the distribution function of a uniform on the interval AB. Okay? 0, 1, so 0 before A, 1 after B, and between a line. Okay? Exactly what I have represented here. And exactly what I write in this formula, in this compact formula using indicator function here. 0 here, 1 after, and between a line. Okay? So just a little remark concerning a particular case that we are going to use a lot. Yes. Suppose that you have A equal to 0 and B equal to 1. That is the uniform on the interval 0, 1. Okay, if I plot its distribution function this way. So before 0 I am 0. After 1 I am equal to 1. In between, I am a line. But what is this line in this situation? What is the equation of this line? But the equation of this line is this one with A equal to 0 and B equal to 1. So you have the identity mapping here. Okay, so 0, identity 1. 0 before 0, identity between 0 and 1, and 1 after. This is a particular case that we are going to use several times in this section. Okay? So this is for the uniform. And more or less, okay, if you know the definition, you are able to do everything with this kind of distribution. But it's important to have this in mind, okay, at the very least for, okay, a rough intuition of what is the distribution function in this case. Constant, line, constant. Okay. Do you have some question on this? It's okay? So if you are okay, let's go to the next distribution. So the next one so just a little remark concerning, because in the discrete case I have given to you concrete examples. Okay? Do you understand why it's not possible for me to give you concrete example or real concrete example for this kind of distributions? In the discrete case, it wasn't that difficult, okay? You flip coin, you roll a dice, so if you modify a little this kind of experiment, you obtain at the end, okay, something that may be related to almost all except the Poisson, but I have shown you that the Poisson is in fact an approximation of the binomial for particular values of the parameter, p small and large, okay? So for this one, in fact, you can take values here in an interval. Okay? So it means that you take a continuum of possible values. A continuum of possible values. And in general, when you do something in real life, you do discrete things. What is the meaning of this? Suppose that I said, I don't know. I take, it's a stupid example, but what may be uniform in the real life, okay, with this kind of thing. Uniform, it's not that easy to find an example, but I come back to what I have in mind before. If you do a measure of someone, you measure something, okay? You may have a way to measure that is very, very, very precise, but you have a precision of your measure tool. It means that below this little precision, okay, you can't do measure. If you measure a speed, it's not possible for you, even if you have very, very, very high-tech tools in order to do this. You will have a little something below you won't be able to go. Okay, so it means that in fact you do discrete things because you have the little, okay, precision level that you can go below, and so you do discrete things. And in fact, all the distribution we are going to see, the continuous one, will be in fact, it's models of reality. It's not reality as flipping a coin, okay, but it will be models of reality. And why we use this kind of models? We use this kind of model because they will be technically better to handle than what we do in discrete time. So you will see typically, not the next example, but the one after, will be the Gaussian distribution. So nobody has seen a Gaussian distribution in real life, okay? But we have seen that it is a model that appears to be a very good approximation in a lot of situations, with the advantage that this density function has a lot of nice properties. And you will see, so that's why we use it in physics, that's why you will use it in finance, that's why you may use it in economics, okay? Not because it appears, okay, naturally in particular situation, but because as an approximation, it's not that bad and easy to handle, okay? So I won't give you particular example for this one, okay, but I've just in mind them as models for particular situations, okay? So the uniform is done this way. Here the exponential. So of course what we call the exponential random variable is related through its density function to the exponential mapping, okay? We will see together that if I can give you an intuition about this one, it is a kind of analogous of the geometric distribution in the continuous case. The geometric and this one are not that different. It's not that intuitive because a priori I have an exponential, so it should be, okay, why not the Poisson and the exponential to be related because I have exponential in their definition. It's not the way it works, okay? Exponential, okay, has some interesting properties that are also fulfilled like the geometric one. And I will do an exercise on this, okay, in the list 5 of exercises. So this is this definition. So let's see what happens. So maybe I can try to plot. So I erase the board, okay? So I can try to plot this density. So of course lambda has to be strictly positive here because I want a density function, so I need something that is positive. If you take a negative lambda, you won't have something that is positive. So I take a lambda that is strictly positive. And my density function is defined this way. Okay, so it's the way I have defined with this strictly positive, why not? So I can write it this way. Lambda exponential minus lambda x for x that is strictly positive. It's exactly what I've written in. Okay. So if I check that it is a density function, what is a density function? Something that is positive. Yes, it is positive. Continuous except at a finite number of points. Also yes. If I want to plot it, okay, approximatively, what happened before 0? 0, when I am strictly negative. Then, what is the value at x equal to 0? Lambda. That is strictly positive. So, and then I am lambda exponential minus lambda x, something that goes this way. It's a negative exponential, okay? So you see that you have something that is continuous, except at x equal to 0. Okay, so continuous except at one point, whatever, okay? I don't want discontinuities in too much points, okay? Here I have it only at one point. The last step is to compute the integral. and I want to prove that it is equal to 1. Okay? So when you do this, you have to be careful about the bounds. Okay? The boundaries of the integral. Here I see that before 0 I am 0. So in fact it's not an integral over minus infinity plus infinity. It is just an integral from 0 to plus infinity. And in this situation, if I am in 0 plus infinity, I know that, okay, I know that I am equal to this. Okay? So I have to compute this kind of integral. So a priori, something that you are supposed to be able to do. Why? Because I have a primitive to exponential minus x, the minus lambda x. The primitive of exponential minus lambda x is exponential minus lambda x over minus lambda. Okay? So here, in this particular situation, the computation of an integral is just related to finding a primitive to the function you are interested in. Okay? So I do it in 2 steps. Limit, so it's an infinite integral, so it will be more or less the last time I will use this, okay, but to show you one time. Okay, so in order to compute this, I want to find the primitive of this term. So the primitive of lambda exponential minus lambda x is minus exponential minus lambda x. Okay, so you have to know the primitives in this course. If you don't know them, okay, you won't be able to do any kind of computation with integrals. Okay? And if I remind, okay, in the reminder concerning integrals, I have given to you a link toward the classical primitives you have to know. So you have to know the primitives of polynomials, you have to know the primitives that are related to exponential, cosinus, sinus, logarithm, 1 over x, square root of x, all these kind of classical mappings, okay? You have nice formulas for the primitives. And keep in mind that to know the primitives is just to know the derivatives, because you compute the derivative in one side, and if you come back to the previous case, okay, you obtain the primitives basically, okay? So you don't need to learn a lot of formulas. If you are able to compute derivatives, you know the primitives. Okay? So, primitives of lambda exponential minus lambda x is this one. And so, if I want to compute my integral here, since I know the primitive, I just have to take the difference of the primitive at capital A minus the difference of the primitive at 0. Okay? So, if you have read, and I hope that you have done the job during the holidays, my little document on integrals, this one is just, I write it this way, and I will write it this way, with this bracket here. I put the primitive inside, and I want to take it between A and 0. It's a notation, you can write it also this way if you want, okay, with the double bracket. I said that this integral is none other than the primitive taking between capital A and 0. And what is this? In capital A, I am minus exponential minus lambda A. And I have minus what happened at 0, so I have a double minus, minus minus, plus 1. So this one is equal to this one. And I am interested in the limit when A goes to plus infinity. What happened for the limit when A goes to plus infinity? You have a negative exponential here because lambda is strictly positive, and the limit of a negative exponential in plus infinity is 0. So of course, at the end, I obtain an integral equal to 1 because this one goes to 0 when A goes to plus infinity. So what I have defined this way is really a density function. Positive, continuous except at 0, and integral equal to 1. Okay? What I call an exponential random variable will be a random variable having this density function. Okay? now we are going to have a look on what is the related distribution function here. What is the related distribution function? From the definition of a density function, the distribution function is obtained this way. Once again, we are going to consider cases because, okay, I have different values depending on the cases here. So typically, if x is less than 0, what is the value of this integral? 0? 0? Because for negative values here, the mapping is 0. So if you consider this integral with x that is negative, you integrate something that is always 0, you obtain 0. And once again, I remark that for very small values, my distribution function is 0, coherent with the fact that the limit in minus infinity is 0. And then, if x is positive or strictly positive, in fact, I have to compute the integral between 0 and x of what? But if x is positive, it is this expression that works. And it's something that I have already computed here. It's exactly this one. I just change, okay, here, small x in capital A. So I have to take this one between small x and 0, and I obtain this one, that is 1 minus exponential minus lambda x. That is exactly what you have in the second blue formula in the slides. This one. Okay, so you have here the distribution function of an exponential, and of course you obtain all the typical behavior of distribution function. Limit in minus infinity 0. If I do the limit in plus infinity of this term, I obtain 1 here. It was my argument here. I have something that is strictly increasing, or increasing, let's say, because I have a negative exponential that is decreasing, but with a minus before. Okay? So if I plot it, if I plot the distribution function here, I can plot it easily. Plot it easily. Then I obtain what? Before 0, 0. Okay. When x is equal to 0, of course, I am continuous. So I am here. And I have this kind of thing here. Okay? So it is something like this. Okay, you have a limit that is 1 in plus infinity, and you have something that looks like this way. You have minus a negative exponential. Okay? Something that looks like this way. So it's not like this, okay? Because I don't want to enter into details, but I know the exponential, okay? Negative exponential, okay? That way, so the negative one would be this one. Okay? So I have my distribution function for the exponential. Okay? And we are going to handle this one also, and you will see in the list 5 of exercises that this one has an interesting property that is the same as the geometric distribution. The property of the geometric distribution we have seen during the previous session. Okay? That is to be memoryless. I have said to you that geometric distribution is not a good choice if I want to model the lifetime of someone. Okay? We will have exactly the same for the exponential distribution. Do you agree? So the last, for the moment, that is the Gaussian. So this one is really, really, really important, okay, and you are going to handle it more than the 2 preceding ones, okay. In more or less all the courses you are going to do, okay, financial 1, economics 1, okay, and so on. So the definition, so here the density function seems to be a little bit more complicated. Okay. So a random variable is said to be Gaussian or normal, it depends, you can use both. Okay, I will use Gaussian. Random variable, so it's a family depending on two parameters, m and sigma square. We are going to see next week that in fact m will be the expectation and sigma square will be the variance. But for the moment, I don't have defined what are variance and expectation in the continuous case. We'll see this next week. So it depends on two parameters, one that may be any real number and the other one that is a strictly positive number. I want something to be strictly positive in order to divide by the square root of sigma square here, okay? So be careful because depending on your background, okay, sometimes you write for a Gaussian, not inside the variance, but the standard deviation. It's not the way I will write it. It will be my notation, this one, and the one that I will use in all the slides and in all the exams we are going to do together. Okay? First parameter m, second parameter sigma squared, that will be in few hours the expectation and the variance. Okay? And you have this definition. You have this definition. So, if I want to check that I have a density function, a priori I have to check three things. Positive, no problem. I have a square root, I have an exponential, so I have only things that are positive. And in fact, I can even remark that I have something that is always strictly positive in this case. Okay? Concerning the continuity, so it's the continuity in the variable x here. I have no problem because I have a negative exponential, I have a square, so I have only mappings that are continuous, and you do compositions of mappings that are continuous. So you have typically something that is continuous. Okay? So no problem with this one. Then integral equal to 1. And here it's a little bit more complicated to prove that the integral is equal to 1. Okay, so I don't know if I will do the computation. Maybe in one exercise it should be possible because I'm missing a result for the moment. That is what we call the change of variable theorem in a dimension higher, strictly higher than 1. Okay, but I can show you the following. So I erase. So to compute this integral is a priori not that easy. Why it's not that easy? Because if you have primitives in mind, okay, you will never see this kind of mapping appearing. That is exponential minus x squared. You don't have a primitive for such a mapping. Or what, by I don't have a primitive, I mean that I don't have a primitive that can be expressed easily with classical mappings. Okay, so you don't have. It doesn't exist, or okay, it hasn't been discovered. So I don't have a primitive for such mapping. So it means that the computation of the integral in this situation is not just a computation of primitives. You have to be more clever in order to compute this integral. It's a little bit more tricky. But just see what I have here. It will be the way to see the change of variable theorem, okay, in one variable, to remind you something that is in my reminder on integrals, okay, but to show you the things. So you need to know this density function, okay, really, something that will be really important in this course. In the probabilistic part and also in the statistical one, okay? So my objective should be to find that this one is 1, okay? And to be clear, I won't do the job today, but I just want to show you that in fact, I can come back because here I have a lot of parameters. I have m sigma squared, so I can come back to one case where, okay, this kind of parameter disappear, meaning that in fact I have only to consider the integral of a single mapping. Okay, so we are going to do a change of variable. A change of variable in my integral. So if you come back to the little document I have written for integrals, okay, you have two tools, in fact, to compute integrals, two classical tools. So if you don't know a primitive, you have two possibilities, two tools in order to try to compute, even if you don't know a primitive. This is the integration by parts formula, okay, and the change of variable theorem. Okay. So what will be my change of variable, okay, in this integral? So change of variable, it's exactly what we have done in the case of sums. I have changed the index, okay, but adapted to the case where I have integrals. I will do this change of variable, y equal to x minus m over sigma, okay? And the idea is that I will consider here sigma that is strictly positive because, okay, it's important to know the sign of sigma because if x goes to plus infinity, if sigma is negative, y will go to minus infinity. So I do the case sigma that is strictly positive. We will do the job at home if you want to exercise for sigma that is strictly negative. I know that sigma is not zero, for sure. So if I apply my change of variable theorem, okay, in this way, so I have a mapping that is strictly increasing, so it is a change of variable. It is, in fact, differentiable without problem. So intuitively, you can say that the dy that will, so I have my dx here, the dy that will appear will just be dx over sigma, that is the derivative of this one in x times dx. Okay? So here it's just 1 over sigma is the derivative of y with respect to x. And then I replace inside. So the limit of x is minus infinity for the lower bound. Since sigma is strictly positive, the same will hold for y. X goes to plus infinity, y also. So plus infinity for y. This one doesn't change for the moment. 1 over the square root of 2 pi sigma square. And here I have some change because you see that you have, if I make enter sigma into the square, you have x minus m over sigma. So I can write it as exponential minus y squared over 2. That's why I do this change of parameter in order to make disappear the x minus m squared over sigma squared in order to replace it by a new variable that is y. And I obtain this one. And finally, I have my dx and my dx that is equal to what? Sigma dy. And in fact, sigma being strictly positive, I have once again a simplification here. That is the square root of sigma square is equal to what? Y. Be careful, huh? If I have this one, what is the square root of minus 2 squared? Yeah, it's 2. It's not minus 2 because the square root is always positive. So a general formula of this one is absolute value. But here I am in the case where I am strictly positive. So since I am in the case where I am strictly positive, I can simplify between these two. And at the end, what is nice is that I have only to deal with, in fact, a single integral that doesn't depend on the parameter nm sigma. So these integrals and this one are equal. It means that if I want to do the job that is to prove that the integral is 1 for all of them in blue here, I just have to do the job for this one. Okay? I can go a little bit further here. What can you say about the clarity of this mapping here? If I want to plot this one, I have a kind of symmetry in the curve here. Which one? So the axis, okay, x equal to 0 is an axis of symmetry, meaning that the mapping is what we call even, okay? Even mapping. So you have something, if I plot, you have something that looks like, okay, that way. Okay? It's what we call the bell curve, okay? It looks like a bell. And I have a symmetry. with respect to the axis x equal to 0. So if I want to compute the integral over the whole r, in fact, it will be 2 times what happened on half of r. Okay? And this one is just 2 times the integral between 0 and plus infinity of 1 over the square root of 2 pi exponential minus y squared over 2. And it means that at the end, if I want to prove that this way I define a density function, what I have to prove, okay, is that the integral between 0 and plus infinity of exponential minus y squared over 2 is equal to the square root of pi over 2. Because here I can simplify the square root, and 2 divided by the square root of 2 is equal to square root of 2. Okay? So I have this one. So if I prove that I have the relation in red, I will prove that I have a density function here. And I said that for the moment, okay, so it is possible and it can be the subject of an homework to do this, okay. It's a nice computation, but it's typically a nice computation that only involves techniques of integrations, okay, and it's not my main topic in this course, okay. So I will suppose that this is true, and if I have time, okay, maybe I will use the proof. I will need, in fact, a proposition that we are going to see later. That is the change of variable theorem in with several variables. Okay. So to conclude what I have said, to prove that I have a density function here, continuous positive is okay, integral equal to 1, a little bit complicated, but I remark that the integral of this one is just the integral of this one. Okay, so meaning that if I want to prove that all these integrals are 1, I have to prove this one that I admit for the moment. Okay? A good remark. An important remark because it's something that we are going to do several times. In this course, okay, so you will have to compute integrals. But you have some material. That is, for the moment, we have seen 3 definitions. Uniform, this one, and this one. From the definition of these 3 random variables, you know that the integral of this type is 1, the integral of this one is 1, the integral of this one is 1. So it means that if you want to do just an explicit computation of an integral, if you recover this one, or this one, or this one, you know that the integral is 1. Typically, if you have the integral only of this term here without this term, but you know that the integral of this one, since the integral of the big expression is 1, the integral of this one will be the square root of 2 pi sigma square. So you will be able, from the definitions from the course, to compute the integral of a large family of mappings. And in general, practically, you will see that in most situations, instead of doing computations, direct computation using change of variable or using integration by parts, you will recognize something that you know from the course, from the exercise we have done previously, and conclude directly that, okay, I recognize a gamma distribution, I recognize a Gaussian one or an exponential, so the integral, this integral is 1 from my course, okay? You will see that it will be the way that, in general, we are going to compute integrals, just using what we know from the course, okay? Because given to you density function is also to tell you that you have a lot of mappings that have an integral equal to 1, okay? Something that you have to keep in mind. So I continue with my Gaussian here. So you have the density function, admitting that this one holds. Why I don't have the formula of the distribution function as in the exponential case or as in the uniform case? Because I don't know. Okay, it's not possible a priori to have a nice formula for the distribution function of a Gaussian. Okay, so you have very nice approximations, but you don't have, it's not possible for me to show you a nice formula with exponential, square root, and I don't know, okay, for the distribution function of a Gaussian. And that's why, typically in the statistical price part, in the statistical part, we are going to need the quantile of the Gaussian distribution. And that's why we are going to use tables in order to find them. That is, tables are just approximation of the quantiles, so something that is based on approximation of the distribution function. Because it's not possible for me to give you, okay, a closed form formula for this kind of thing. Okay? So uniform exponential Gaussian is what we are going to work with for the moment. Okay? And the other one that I will do in exercise, okay, will be the gamma, because the gamma will be a special, will be an extension of the exponential, will be an extension of a lot of distributions seen in the course. Okay? So that's why it will also be considered as course, okay, for this part. So let's do the break, okay? And after I will handle a little this Gaussian because it is very... So now we are going to see, we are going to do exercise, in fact. They are inside the course, but, okay. We won't see theory more things today, but we are going to train a little what we have done previously, okay? So typically in the proposition 13, you have something that is really interesting concerning the Gaussian distribution. Gaussian distribution will be stable by a affine transform. So if you finally transform a Gaussian distribution, you will still obtain a Gaussian distribution. In other words, if you have n01, if you do m plus sigma x, you obtain an nm sigma square. If you have an nm sigma square, if you compute ax plus b, you have a new Gaussian with known parameters. In this one, it is also possible to pass from an nm sigma square to n01 by this affine transform. Okay? So I can finally transform a Gaussian and I will obtain a Gaussian. So I will do the job. And we are going to see that the main tool will be the relation between the density function and the distribution function. So the tool we are going to use for the moment here is the distribution function. In a few minutes you will have another tool to do, but in fact I prefer you to be able to do what we are going to do for 3 or 4 examples now than to learn stupidly a result that you are going to forget in 2 hours. Okay? So the methodology is better than to apply the result we are going to see just after. So I start from n01. So when I have an n01, I have a density function. That is what? But it's exactly what I have in blue for m equal to 0 and sigma equal to 1. Okay, so I have a simplification in this density. So the density in this case is given by 1 over the square root of 2 pi exponential minus x squared over 2. This one. Okay? I take m equal to 0 and sigma equal to 1 in this expression, and I recover exactly what I have written on the board here. And I am interested in what happened for m plus sigma x. And my objective is to prove that m plus sigma x as follows the nm sigma square, that is as this density function. Okay? My job. So I am interested in, let's give it a name, y equal to m plus sigma x. In order to find the density function of y, okay, we are going to use this result, the proposition 12 here, that tell me if I obtain the distribution function and if it is sufficiently regular, in order to obtain the density, I just have to compute the derivative of the distribution function. Okay, so it's the statement B of the proposition 12 that we are going to use together. Okay? So let's have a look on the distribution function of y at the point x. This is the probability that y is less than x. And of course, y has a particular definition, that is to be m plus sigma x. So I replace. And the idea is in fact to express everything using what I know, that is, using the fact that I know the distribution of capital X. Okay, so we are going to try to make appear the distribution function of what we know, that is the distribution function of X. Okay? But I have just to be careful in this situation, because if I want to isolate capital X, what I will do? I will do minus m and divide by sigma. But you know that when you do, or when you add something to an inequality, it changes nothing. But when you multiply or divide by something, this something has to be positive if you don't want to change, okay, the side of the inequality. So a priori, we have to take into account two cases: the case where sigma is positive here strictly, and the case where sigma is strictly negative. I will do the job for sigma strictly positive, and at home, to see if you have understood, you will do the job for sigma strictly negative. The only thing that it will change is that we have to change the side of the inequality. Okay? So I do the job. So first case, let's say, and it's the only one that I will do, the case where sigma is strictly positive. At home, you will do the case sigma strictly negative. That is exactly the same thing. So if sigma is strictly positive, I can write the following. The distribution function of y at the point x may be written as the probability that x is less than x minus m over sigma. I don't change the side of the inequality because my sigma is strictly positive. So when I divide by it, it changes nothing in terms of side of inequality. But here, I recognize the distribution function of capital X at a particular point. Okay, so I continue here. It's the distribution function of X at the point, what? By this point, this new point, X minus m over sigma. Okay? So I have this one. And what I know that f capital X is the distribution function related to n01. Okay? So I have said to you that unfortunately I don't have an explicit expression for this one, but it's not what I need here. Okay? The idea is to use the statement B of the slide here, of the proposition 12. That tells me the following. If the distribution function is continuous and regular, okay, then to obtain the density, I just have to compute the derivative. Here, I know that f of x is regular because it is the distribution function of or associated with the n01, the Gaussian distribution with parameters 0 and 1. And what I have inside here is another mapping, but that is also very regular because it is a line, in fact. Okay? It's a fine mapping. So when I do the composition of something that is regular with something that is regular, I have obtained something that is also regular in the sense that it is continuous everywhere, and here, in fact, C1 everywhere. Okay? I don't have point of discontinuity in the density. So, if I want to compute the density function of this one, I just have to compute the density function of this expression. Oh, excuse me. If I want to compute the density function of y, I have to compute the derivative of the distribution function of y, and so to compute the derivative of this expression here. It's only what I have to do. So, from the proposition 12, statement B, the density function of y is given by the derivative of the distribution function and the derivative of the distribution function that is equal to the derivative of this mapping here. And I have simply, so if you want I can put a parenthesis, and it's the derivative of a compound mapping. And you know the formula, f j prime is equal to f prime j times j prime. Classical formula for the derivative of a compound function. So it's exactly what we are going to apply with small f, that is f of capital X, and small j, that is x minus m over sigma. So when I compute the derivative of capital F of x, what I obtain? the density. So when I compute this derivative, I have the density of x, because the derivative of this one is the density, at the point x minus m over sigma, that is my j here, and I multiply by the derivative of what I have inside, and the derivative of what I have inside here is that simple, that is just 1 over sigma. Okay? And in fact, now I have finished the job. The only thing I have to do is to plug what is the density of x, and I have this expression for the density of x. So we are going to plug inside. It is 1 over the square root of 2 pi. Exponential minus what? But instead of x inside, I replace by x minus m over sigma. So it is x minus m over sigma square over 2. And I multiply by 1 over sigma. If I handle a little this expression, I can write it this way. If I make inter sigma into the square root, I have the possibility to do, because sigma is strictly positive. If I want to make it enter, I have to put a sigma square in the square root. Okay, so I have 1 over the square root of 2 pi sigma square, because the square root of sigma square is the absolute value. But the absolute value, that is in this case sigma, because I have supposed sigma to be strictly positive. And then, so I erase this formula. And then I have this expression here, and I will just extract the 1 over sigma from the square to obtain exponential minus x minus n square over 2 sigma square. And what do you see? I see that what I have obtained is this one, exactly. Okay? So since I have proved that the density function of y, is equal to this expression here, I have proved that y follows nm sigma square. Okay, so I have proved the first statement, that is, if x follows the n01, m plus sigma x follows the nm sigma square. Okay? So it means that, so from a practical point of view, it is something that is interesting, yeah? Because it means that, suppose that you want to generate a n01 with a computer, okay? Or suppose that you want to generate an nm sigma square using a computer. For the moment, maybe I will have time to speak about this point, but it's not my topic in this course. But suppose that you want to do this. The intuitive meaning of this proposition is that if you are able to do the job for n01, you will be able to do for nm sigma square, because you just have to apply this little transform here. So from n01, you easily obtain an nm sigma square from this transform. Okay? We have tools in order to generate n01, and so we have tools to generate nm sigma square for any m and any sigma. Okay? So this is the intuitive way. Another way to see this is that if you have a property for this one, in general you will have also a nice property for this one from this linear transform. Okay? And typically, if you do a reasoning in terms of distribution, to consider nm sigma square, or to consider n plus sigma x with x being a n01, is completely the same. That is, if you want, we will see later, to compute the expectation of nm sigma square, it will be sufficient to compute the expectation of this one, knowing that x follows the n01. If you want to compute the variance of nm sigma square, it will be sufficient to compute the variance of this one, knowing that x follows the n01, and so on. Okay? In all the things that we are going to do later, in general, if we want a result for this one, we'll just say that, in fact, this one is just this one for x following the n01. Okay? So I have done the job. Okay? And now the two remaining things are just a little consequence of what I have proved now. Okay? So are you okay with my reasoning here? We are going to see that we are going to do this 2 more times today with other case, so it will be, I think, okay for you at the end of the session to do this kind of thing. That is how to find a density function of something, okay, from its distribution function. Okay. So may I erase? Yeah, I erase. Second statement. I suppose that X follows n m sigma square. Okay? And I want to prove that if I transform it linearly, so it's a generalization of what I have obtained previously, but here I don't start from n01, I start from nm sigma square. I transform it linearly as I have transformed this one linearly, and I obtain a new formula for the parameters. Okay, so what I have proved for the n01 will also be true for a general Gaussian random variable. That is, I am stable under affine transform, and I can find explicitly the parameters of the affine transform. Okay, so I am interested in ax plus b. So it should be possible to do exactly what I have done previously, but the idea is not to do this. Okay, because I have proved the previous result. I have proved the previous result, saying that in fact my x that follows nm sigma square may be seen as something of this form, m plus sigma, let's say x tilde, where x tilde follows n01. It's the way we are going to do the job, because I know that both of them have the same distribution, and it's what I am interested in here. Okay? So I can write my capital X, and this is coming from the statement small a we have proved previously together. Okay? And now it's finished, because I replace what is x. X can be written as a times m plus sigma x tilde plus b. I can write it as a sigma x tilde plus am plus b. And if I use the statement A we have proved together, here I have n01. I multiply it, or I transform it linearly with this parameter before the x tilde and this parameter, okay, that is the translation parameter. And so I obtain what? From the proposition A, from statement A, what happened for ax plus b. So if you want, you have here, you have a new m that I can call m tilde. You have here a sigma tilde, and you obtain, you just use the statement A with my new m and my new sigma. So I replace, and I follow what? I follow a Gaussian with parameter am plus b, okay, and a second parameter that is a square sigma square. That is exactly what I want to obtain. Okay. It will be the same for the last one. Are you okay with this? Yes or no? I use the result of statement A with this new set of parameters. I don't do more. Do you agree? If you agree, I continue. In the first statement, I show you how to pass from a n01 to a nm sigma square. The small c is a kind of converse. If I start with a nm sigma square, how to make... So we can go back to proposition 1, right? What is this one, you mean?
No, from the third one to the first one.
Wait, it's exactly what I say. So from this one to this one, yes, if you want, it's a kind of converse, okay? How to pass from n01 to nm sigma square, and here how to pass from nm sigma square to n01. In fact, you have to invert the transform if you want, okay? So I agree with you that you have a complementarity between these two statements. And the way we do is just to use what we have obtained previously here. So I start from a nm sigma square once again. My nm sigma square, I will write it as m plus sigma x tilde with x tilde following n01 from the proposition 1. Okay? And then I want to transform it this way, xm minus m over sigma, in order to prove that I have a n01. So I am interested in x minus m over sigma. I replace x by this transform, and I obtain m plus sigma x tilde minus m over sigma. And I obtain what? Well, I have done the job exactly to have what I want. That is, I have simplification between n and minus m. I have simplification between sigma and 1 over sigma. And I obtain at the end simply x tilde. So this one is equal to this one. And I know the distribution of this one, that is just n01. Implying that this one follows n01. That is exactly the result I want to prove. Okay? So this proposition will be helpful, in particular in the statistical part, if you want to pass from nm sigma square to n01 or conversely. But in general, we have a general Gaussian random variable, and you want to transform it in order to obtain a n01, because I have said to you that I don't know the distribution function of this one. Okay? If I want to know it, I have approximation, and so I have tables. You imagine that it's not possible to have a table for any set of parameters. But the meaning of this one tells us that if you have done the job, that is, you have a table of approximation for the distribution function for n01, just applying this little transform, you will obtain exactly what you want for n m sigma squared. So it means that you need simply one table, the one of the n01, in order to have the table of all the Gaussian random variables. Okay? So this is the intuitive meaning of this proposition. Okay? So I have this one. So it's result that you have to know, because you are going to use them, okay, strongly, not only in this course, but in finance, okay, in other topics, in statistics, and so on. Okay. Questions? If you don't have, I want you to try to do at the very least the first one here, by yourself. Okay? I start from n01, okay? And I want you to find, so PDF, and if you have a look on what I have written before, it's not something I have insisted on. So PDF, it's just for probability density function. It's not the format of my file, okay? It's just probability density function. Okay? So here, it's exactly what I have done. Here, what I have done, in the previous case, I start from n01, I transform it linearly, I obtain the distribution of the transform. Here, I want you to do the same with another type of transform, that is to take the square. Okay? Question? Yeah. Yeah?
It would be alright to do 1 minus.
Yeah, of course. You have to come back to the distribution function of x. So, if you are in the negative case here with sigma that is negative, when you are going to compute the distribution function of this one, you are going to obtain the probability that x is greater than x minus m over sigma. And you will express it as 1 minus the probability that x is less in order to compute the derivative. It's exactly what you have to do. And you will obtain the result.
Yeah, but we just make the reaction in the first
Hmm?
enough distribution.
Is?
Then we are not doing this, we are doing 1 minus this.
No, I know. It's not possible to have 1 minus x. Now you compute the derivative, so the constant disappears. Okay? If you compute the derivative of 1 minus the distribution function, you won't obtain 1 minus the derivative of the distribution function. You will just obtain minus 1 of the derivative of the distribution function. And you will see that the minus will simplify, in fact. Okay? And be careful, huh? When I ask you to compute a density function, at the end, be sure to obtain something that is positive. Okay, if you don't obtain something that is positive, it means that you have done a mistake, huh? For sure, because you have to be positive, continuous, integral 1. If you are not positive, mistake. So you have to check your computation and see where you have done a mistake, because you have done a mistake for sure. It's like if you obtain a probability equal to 2. I have a problem, okay, for sure. I try to do. I'll leave you, let's say, 10 minutes to do this by yourself. It's exactly the same methodology than the one I have used previously. So, what I want you to do, I start from N01 and I want the density of the square. It's a distribution that will be considered as a distribution from the course. It's what we call the chi-square distribution. And you will see it appear in the statistical part, in fact. Okay? The square of a Gaussian. So, with my notations here, x follows the N01, meaning that you know perfectly what is the density of x. And I want you to find, I want the density of z that is equal to x squared. Okay? It's what I want you to do. And the objective, in fact, and the techniques will be the one related to this proposition here, this one. Okay? So you are going to try to find the distribution function of z. And once you will have found the distribution function of z, you will compute its derivative that will give you the density function according to what I have written here. Okay, so I just want you to do by yourself to see what happens. Okay? So do it with a pen, with a paper. Okay. So I want to compute the distribution function of z. This one. Okay? So I said first that z is a square. So there is one case where it is very easy to compute. Which one? For what value of small x, this probability is very easy to compute. For 0, yes, but you have more than just for 0. Yeah. So if x is negative, this proba is 0, always. The probability that the square is negative, okay, so can be the probability that I am equal to 0, but since I am a Gaussian, the probability to take a particular value, 0. Okay, so I don't deal with this case, okay, because it's very easy to handle it at the very beginning of the process. It's like, okay, if I see my curve here, that is the curve of the square, if I ask you when I am strictly less than this level, but nowhere, because I am positive, okay? But now if I use something that is strictly positive, if I tell you when the square is less than this level, you see that you have this interval here with what I have here, that is the square root of x, and here minus the square root of x. Okay? So if x is strictly positive, yeah, the square less than x means exactly that x is greater than minus the square root of x and less than the square root of x. Okay? So if I continue here, this is equal to 0 if x is negative. And when x is strictly positive, I can express this kind of probability by using what I know from the distribution function. That is what I have said at the very beginning of the session. That is this statement here. But I have said to you that in the continuous case, you don't mind about what are the bounds of the interval. You can put strictly or greater, less than, strictly less, whatever, because I have this. All of them are equal. So here, the probability to be greater than minus the square root of x and to be less than the square root of x may just be expressed as the distribution function of x at the point square root of x minus the distribution function of x at the point minus the square root of x. I have this one. And at this stage, I can't do more because I am not able to express explicitly the distribution function of n01. So a priori, what I say here has nothing to do with probability. It's just, I have a look on the square and see what happened. What is the meaning of b or for a square to be less than a number? Two situations. When I am negative, okay, I have just 0. And when I am strictly positive, I have to be in the interval square root of x minus square root of x. So now this one. I have to check that I can use the small b in the proposition 12. So first I have to check that I am continuous. I have the only problem I may have for the continuity here is that at x equal to 0, okay, I have a problem because at this point I change my definition. Before it's 0, after it is this one. So what happened at 0 for this expression here? It is fx of 0 minus fx of 0, but that gives 0. So fx is continuous without problem. So I'll write it this way, fx continuous because fx of 0 minus fx of 0 is equal to 0, meaning that at x equal to 0, what you have here and what you have here coincide. And of course, since I want to use the proposition 12, I will have to show and to see in your copy the hypothesis that allow me to use this proposition. So fx is continuous in French. Continuous because I have this. In order to apply the result, I have to check where it is C1. It is C1, so here no problem, because it is always equal to 0, so I am with a very big regularity if I am constant, okay? And for this one, what I know? I know that the distribution function of a Gaussian is C1 everywhere, okay? And inside I have the square root for x strictly positive. So the square root mapping is this one, okay, square root. And what can you say about the differentiability of the square root mapping? Everywhere? Now, it is differentiable except at this point here. Okay, I am smooth everywhere, but here you see that you have a little angle here. I have something that is not smooth at this point, and the square root is not differentiable at 0. So here you have something that is f of x is differentiable on R except for 0. But it's not a problem because in my statement I don't mind about what happened at a finite number of points. Here I have a single point where maybe it is not differentiable. It won't be. Okay? So I have this one. And so I can use my result. The density function of what I am interested in, that is z, will be obtained as what? As the differential of the derivative of the distribution function for the points where I am differentiable and 0 otherwise. So here, when you compute the derivative, what do you obtain? The derivative of this mapping here. 0. Okay? At x equal to 0, I don't mind, okay? And for x strictly greater than 0, I have to just to compute the derivative of this expression here. Okay? So using proposition 12, the slide, I can say that the density function of z at the point x is equal to what? Two things. 0 if x is negative, and equal to the derivative of this one when x is strictly positive. That is fx square root of x prime minus fx minus the square root of x prime. And so my problem here is just reduced to the computation of the derivative of a compound function, basically. I read this. You see that I check that I am able to use the theorem. And now it remains to compute. So here it's for if so I compute the derivative of this part here. Okay. So if x is strictly positive, I am interested in the derivative of this one minus the derivative of this one. Okay, so it's a compound function. So f compound with j. Okay, so the derivative of the distribution function is the density function. So it is fx square root of x multiplied by the derivative of the square root. What is the derivative of the square root? 1 over 2 square root of x. Okay? Okay? Minus the derivative of this one is the density at the point minus the square root of x, and I have to multiply by the derivative of minus the square root of x, that is just minus 1 over 2 the square root of x. At the end, I can write the things in the following way. It is 1 over 2 the square root of x, density of x at the point square root of x, plus density of x at the point minus the square root of x. Just put into factor. I have a double minus here and here, so I have a plus here. Okay. And I have to close my parentheses. Okay. Now to conclude, it remains to say what? I know what is the density of x. Okay? The density of x, because x is in my statement n01, f of x small x is equal to 1 over the square root of 2 pi exponential minus x squared over 2. Okay? So I have just to plug inside the square root, or to plug inside minus the square root, but since I have a square here, to put this one or this one will give rise to the same thing. This one, by the parity of this mapping here, it's an even mapping here, I obtain 2 times fx, the square root of x, because if you put inside the square root of x or minus square root of x, you obtain exactly the same thing. Okay? So I have 2 times the same value, and now I just have to replace, to plug inside. So I obtain what? 1 over the square root of x. Okay, multiply by 1 over the square root of 2 pi exponential minus what? By the square of the square root, that is minus x over 2. So I know my density function will be 0 if I have negative, and if I am strictly positive, it will be the derivative of this one that is given by this expression here. And at the end, I can summarize what I have obtained this way. At the end, the density function of z at the point x is equal to what? Is equal to 0 if I am negative and something if I am strictly positive. So I put an indicator function of r plus star x, meaning that my x has to be strictly positive if I want to be not 0. And then I have something that I can write as 1 over the square root of 2 pi x exponential minus x over 2. You will see later on that this distribution is what we can consider as a classical one. Okay? It is denoted symbolically by the Greek letter chi. Okay? Chi square of parameter 1. That may be written this way. Chi square of parameter 1. So, and the definition I can give of a chi square of parameter 1, it's the square of a n01. What I call the chi square of parameter 1 is the square of a Gaussian distribution. It's just the name, violin, okay? In purple, you have this. Okay? And you will see that in the list, if I remind, maybe in the list 5 or 6 of exercises, okay, we are going to deal with the chi-square distribution with a parameter that is not necessarily equal to 1, okay? And you will see that the way, so please stay every time, between every break, you are going to go out. Like 1 minute, but 1 minute plus 1 minute plus 1 minute, okay, but go, okay, but not every day and during every session, okay? Except if you have medical problem, it's possible, no? And in this way, I have to say nothing. It is just to go out to smoke a cigarette or something like this, okay? Okay. I will cut the video. And you will see later on that what I will call a chi-square distribution of parameter n will be the sum of the square of n independent Gaussian. And here we have a single one, so n equal to 1. Okay, but we will see this later. Okay, with my computation? So, in fact, if you have one problem, you don't have a problem with this proposition. You have a problem with the beginning of the reasoning, that is, okay, how to transform x squared less than x into something that I am able to compute. Okay, so you have to train a little, but it's a priori nothing to do with the result we have seen together, but more things to do with the way to understand what is the square mapping. Okay. Allez, to conclude the today's session, I will do by myself the last, okay, and see you a few words on this proposition. So I won't comment that much this proposition, because for me it's a classical proposition, okay, that I write in the course, but it is not meaningless, but it is useless, because if you are able to do what I have done, it's very short to do this. You don't need to learn this formula. Okay, yeah.
What is it?
Probability density.
No,
You know.
I know that. But it cannot be probability because.
No, it's not a probability. It's not a no.
I've concluded that because.
Yes, I have said the definition. It's a definition I have given previously.
But what can we conclude from the graph?
What you can conclude from the graph? Nothing. Or do you want to conclude something from the graph?
Well, if you have a function, you put a graph,
Yeah.
and you must conclude.
It won't be possible for you to see if it is a PDF or not. You can exclude pages. If you have a graph with part that is negative, you are sure that you are not a PDF. If you are a lot of time not continuous, it won't be a PDF, but to see on the graph if you have an integral equal to 1, except for very, very basic function as the case of the uniform, you won't be able. You have to compute.
Yeah, no, but what I mean is what's the utility of this? Because when, for example, when you do a graph, the velocity, you know that in this point
The
of
graph of
time,
what?
velocity
Velocity of what?
of a car, for example, you know at this point it has a velocity of 5 kilometers per hour.
Yeah, it's a what?
And every graph tells you something.
No, because you take a, yes, the graph of the velocity of a car So I will explain what happened. Maybe in the white note. So I have to erase a little if I want to explain. So a question that is a good question is, okay, I have defined a PDF, but I have seen that it's a tool. It's a tool that will help me to compute probabilities in some situation. Because with the PDF, I will be able to compute all the distribution function and so the probability of belonging to any type of interval. Okay, but I be more precise with your question. So a question was, what is the intuitive interpretation of the PDF? Okay? If I consider this, okay? So I have the probability that I am, but not very far from small x. So if you take your example of velocity, okay, so if x is the velocity of the car, you are going to see, okay, if x is 100 kilometers, the probability not to be very far 100 kilometers, okay? So if I want to compute this one, I can compute it using the distribution function, okay? And what I am interested in, if you want, when you are looking to a density function, okay, is to say what happens when epsilon goes to 0. What happens when epsilon is really very, very small, that is, goes to 0, okay? And I can see that if I take this expression, the limit when epsilon goes to 0 of the probability that x is greater than x minus epsilon less than x plus epsilon, okay, is equal to what? So I have to divide by something if I want to make the limit exist. But this is this one. So if I come back to your example, okay, of car velocity, you have the curve telling you, okay, what is the probability that, let's say, the car velocity is less than a speed, an arbitrary speed, okay? But the density function will tell you, okay, some knowledge about this ratio, where here you have the probability to be very near from a given speed, okay? So in other words, if I use a kind of approximation, you will have that this one, if you want to approximate it concretely, you will have 2 epsilon. What I have said here, in fact, is just the fact that the density function is the derivative of the distribution function. But intuitively, it's this one. You are interested in this kind of probability and the behavior of this kind of probability when epsilon belongs and tends to 0, okay, toward 0, and then you have this.
How is that possible if the probability in an exact point is 0? Shouldn't the limit go to 0?
Of course, the limit of this one goes to 0, the top. That's why I need to normalize it. So this one goes to 0, okay, for sure. And for this, I have said a mistake here. Then goes to 0. No, we have this.
Because something times 0.
But you have, okay, you have a limit. So if I consider each step separately here, this one goes to 0. This one goes to 0 also. So I have 0 over 0. A priori, I don't know. When I have 0 over 0, it can be anything. But here, in the case, in this particular case, the limit exists and it's equal to, it's one way to define, if you want, the density function. Okay? You can plot, of course you can plot. It's not what I asked you to do. You can plot distribution function, you can plot density function, but you can plot probability mass function for Gaussian or for continuous distribution. Never. Probability mass function, in fact, is always 0. Okay? So don't see f capital X of small x, this one, as the probability that x is equal to small x. It's not that this, not at all. Okay? It's something that gives you the behavior of this probability when epsilon is small. Okay? So I am agree that the first time we see that, okay, we have, okay, mapping, and the probability that this mapping take a particular value is 0. The natural first impression we have is that it is always 0. Because, okay, each time I want her to take a particular value, the probability is 0. But what you need to have in mind is that contrary to what happens in the case of discrete random variable where you take some particular value with a probability that is strictly positive, typically for a Bernoulli to be 0 is 1 minus p, to be 1 is p. It's not what happened in the continuous case. In the continuous case, okay, what you are able to control is the probability that you belong to an interval, okay, that is not empty. It's exactly what you do. So I hope that it is a little bit clearer that way. But in fact, what I have written here is simply what I have said when I said that the density function is the derivative of the distribution function. It's what I used to say this. Okay? 2 minutes. So density function will be something that may, in fact, help us to understand what are the probability of this kind of interval. Okay? But at this stage, and for what we have done, okay, so in general, in the situation, you are going to consider something that you observe, and you will do an hypothesis. The hypothesis that, okay, this random variable, this random phenomena is modeled by a particular distribution. After, it will be possible to see if this choice is clever or not, okay, but it's a model of things, okay? So I have already said that in real life, you don't see anywhere an exponential distribution. You don't see anywhere a uniform one, okay? You don't see a Gaussian. This is just approximation of particular situations that works in many of them, okay? But here, for the moment, it's not my topic. I don't want to do modelization. You will do if you do finance, you will do if you do economics. My job is to just to give you the tools in order to be able to do clever things later on. Okay, so it's the way. But I will finish by this today because it's time and I have to finish 10 minutes before, okay, because I see that I have Elena somewhere here. So I want you to do this by yourself. Try to do this thing by yourself. The second example, it's exactly the same thing. So I have the exponential. You know that the inverse of the exponential is the logarithm. You are going to use this. And be careful about the cases. And you have u that is a uniform on the interval 0, 1, and you know the distribution function of this uniform. 0, identity, 1. Okay, so it's what you need to do in this route. And I will continue, okay, next week with a pair of Gaussian, pair of random variable and so on. So see you next week.